So yes, I'm going to be talking about the 2D graphics side of things. So WebGL isn't necessarily just a 3D API. It's actually a 2D API which has a lot of functionality that you can use to make 3D graphics, but there's nothing inherently 3D about it. At the end of the day, you're drawing onto a flat 2D screen, and it's up to you whether you choose to draw a flat image or you try and draw a cube or something that's got some kind of perspective. So often when I talk to people about WebGL, they think, yeah, that's for 3D content, and that isn't something that I'm doing, so I'm not interested. And when they think about doing 2D content, they think about using just the Canvas API. So what I'm going to try and show you today is that if you use the WebGL API, using the Canvas element, then you can actually do quite a lot of interesting image processing in a way that you would just not be able to do using the standard Canvas API. It makes a lot of the sort of manipulations you're used to from things like Photoshop very kind of simple. Like a lot of them are just like one line of code, just one mathematical function, one transform, and it runs very, very fast compared to the Canvas API. Okay, so this talk is going to be split into two halves. I'm first just going to give a primer in how the WebGL pipeline works. So this is going to be reasonably technical, quite high level. If you don't understand everything I'm saying here, don't worry too much. It's more just to give you some sort of background. And then I'm going to actually dive into a bunch of examples where I'm going to show you how you can do things like rotations or you can warp the image. And again, this is going to be quite technical as well, quite mathematical. And if you just take away just one thing, then I'd like that to be sort of how simple and how quick it is to do these kind of things. It's not like pages and pages of image processing code. It's just normally one line of code. And this kind of flexibility is very kind of useful. Okay, so WebGL basics. So to get a WebGL app running in your browser, the first thing that you need to do is create a Canvas element and ask it for a WebGL context. Once you have this context, you can start doing WebGL calls and start using the API. But before you actually draw something, you need to upload some kind of geometric primitive to the graphics card, which will be displayed. So the simplest thing you can draw is just a single triangle. And in this case, we're going to take two triangles, put them together, and draw a quad, which is just a square on our screen. So once you have this quad on your screen, it won't actually do anything. You need to supply two programs to the graphics card, which are called shaders. So the first shader is called the vertex shader, and this is used to manipulate the geometry of your quad. So you can use this to rotate your quad, to scale it, to displace it, all these kind of things. The second shader is called the fragment shader, and this is a program that's invoked on every pixel on your canvas. So this tells you kind of, and tell the graphics card how you would like to draw your shape once you've described sort of the geometry. So here you might just draw a solid color, or you might draw an image or something a lot more complicated. So once you have these two programs, then you compile them into a shader, and this is all done within the browser, so it's not something that you have to do offline and then link into the program. It's just a string in JavaScript that you pass the API. So at this point, you now have a working program, and you actually do get something shown on screen. But to do something useful with this program, you need to pass in some kind of data that changes on every frame to give you some kind of interactivity. So this is kind of like the glue code between your JavaScript world and your WebGL world. You kind of think of these as just like channels in between these two programs. So you pass different types of variables into your WebGL program. So the first type are attributes, and these are just parameters that are passed on every vertex in your quad. And then the second ones are uniforms. So these are kind of global variables which are passed to the whole program. So this might be the overall color of something, or it might be how bright your light is, or something else like that. And then finally, all this is outputted onto your Canvas element, which is just like any other element in your web page. You can scale it using CSS, you can move it anywhere, you can just treat it as just another tag. Okay, so that was very high level. I'm just going to dive into these a little bit deeper to give you more of an idea of what I'm actually talking about. So first of all, the Canvas element is created in a pretty standard way. You just ask a document for a new element, a Canvas element. You configure its size based on either, well, if you want to have it be full screen, you can just make it the same size as the document. If you want to put it in some kind of container div, you can do that as well. And then finally, the important bit is that you ask the canvas for a WebGL context. So that's this bit here at the bottom. So once you have this context running, then you need to create your quad. So this is what I mean by a quad. It's just 4 vertices, which are arranged into 2 triangles. And they're defined in a coordinate system called clip space, where the coordinates run from -1 to 1. So the bottom left corner here is -1, -1, and here you have 1, 1. And defining this in JavaScript is pretty easy. You just create an array of these parameters. So this one here is just the first triangle, and then the second one is this triangle up here. Okay, so this quad you then take, you upload it to the graphics card, and now you have to define your shaders. So the vertex shader is used for manipulating these vertices that we define in the quad, and then the fragment shader is used for drawing each individual pixel. So what do they look like? So the vertex shader looks something like this. It's just a simple program that has a main function, and its sole responsibility is to set some kind of value to this GL position variable. And you get various things passed into your program. So you get passed in this coordinate, which is just the position that we defined for this vertex. And you can use this to set this GL position. So what we're doing here is nothing but taking the position of the vertex and setting it to this GL position, which then tells our graphics card that is where we want to have this vertex. I'll get back to what this V coordinate does in just a second. So now a fragment shader. This is a bit more interesting. So here, what the graphics card is going to do is it's going to execute this program on every single pixel within our canvas. So it's going to sort of start across the top here, scan across the top, and then do all the vertices that we have, all the fragments that we have within this canvas. But because it's a graphics card, it's not going to do this sort of one by one in a slow, sequential fashion. It's going to do it all in parallel. So this can run at 60 frames per second, no second, because it's all very, very massively parallel. So the interesting thing to notice here is that the color that I'm setting on this canvas is based on the coordinate. But rather than just having black in one corner, red in one corner, yellow and green in the other corners, then it smoothly changes from one color to the other. And what's happening here is that the graphics card is automatically interpolating the value of this coordinate across our entire image. So that's what this varying parameter here is doing. So when we are in the vertex shader, then we set some value on each vertex. So in this case, we're just setting the coordinate, and we set it to this V coordinate varying parameter. And then what the graphics card is going to do, as it sort of goes bit by bit between our vertices, it will smoothly increase the value of that parameter to give us sort of a gradual increase from one side to the other. So for example, the value of this coordinate is -1, -1 here. And I'm just mapping the first component to the red channel. So in this half, it's all black because it's a negative number. And then as it starts getting bigger and bigger towards the right-hand side, then the red color channel increases and gets larger. So we have pure red here, pure green here, because this is the green channel. And then here we have both red and green, which gives us yellow. Okay, so this diagram is just to give you even more of an idea of what the kind of data flow is like in this sort of program. So in JavaScript, we define some sort of attributes and some sort of uniforms. So these can just be any parameters. They can be colors, they can be vectors, they can be textures. So, well, not with attributes. Attributes is just something that are a per vertex number. So the attributes are passed only into the vertex shader, and they don't get passed into fragment shader because it doesn't make sense to have them there. They're defined per attribute, per vertex. So you don't have vertices in the fragment shader, so it doesn't make sense to define them there. Uniforms are your global variables, which go both into the vertex shader and the fragment shader. So these are just overall control things that you can pass into both. And varyings are these smoothed attributes. So it's something that we set in the vertex shader, and it's automatically smoothed for us and accessible in the fragment shader. Okay, so I hope that made some sense to you. If it didn't make too much sense, don't worry. The more interesting bits are the actual sort of image processing techniques, and this is more kind of background to show how you kind of like would build this kind of application in the browser. So it does sound quite complicated, but you don't need to use too many frameworks to do this. Like to just write this in vanilla JavaScript takes maybe 100 lines of code, and then you're up and running. So you don't need to use some complicated framework like Three.js. You can just code this up yourself. Okay, so now I'm going to switch to a demo. So for this, I'm going to be using Firefox, which has got a very useful feature in it, that it has this in-browser shader editor. So you can edit the shaders that you're uploading onto your graphics card just from within Firefox and see things update in real time. So can you see the text on the right-hand side well enough? Yeah, good. Okay, so on the left, that's my actual quad. This is my my web page. And on the right, this is the Firefox developer tools, which is showing both the vertex shader and the fragment shader. So here at the top, this is the vertex one. And we're passing in at the top this coordinate. And all we're doing is setting the GL position to that coordinate. And for example, if we multiply this by some number that's more than 1, then we can scale this quad that we have here on the left. So what this is doing is taking the values that were, say, 1, 1, and making them 0.8, 0.8, and that means that we scale our image down to something smaller. So another thing that I've built into this demo to make it more interactive is these controls here. So all these are just controlling some JavaScript parameters, and then these get passed on into the uniforms. So those are the variables within our shaders. So what I can do is define a uniform in the code here, like this. So because this is UA, this is just going to be mapped to this value here. And then if I multiply this coordinate by it, which is our scaling factor, then as I move this slider, then what it does is it changes the size of our image. And in all the demos, I'm going to be using these kind of parameters to control the various image processing things that I'm going to be doing. Okay, so just now quickly I'm going to describe what this fragment shader does. So this is taking in this V coordinate, which has been automatically smoothed for us by the graphics card. And it's just setting it to this color parameter here. So this color here is a 3-dimensional vector where each component is a color channel. So if we, for example, take the X channel, or you can even just use R and set it to 0, then we won't have any red color in our image. Or if we set the color to be just entirely green, like this, so we only have green in this channel, then we just get green across the whole image. So of course, this isn't so interesting. We want to load in an image so we can actually manipulate it. So the way that we do that is that we pass in a texture as a uniform. So I've already bound this all in JavaScript, so I don't have to kind of do all this typing. So what this sampler 2D thing is, it's basically a link into our texture. So it enables us to look up a single value of a pixel within our image. So if I just set our color to some location in our image, so I'm just going to pick the top left corner. Then what this is going to do is it's just going to take the top left pixel of our image and draw it across our whole canvas. And as I change an image, it's going to give us a different pixel. So this isn't what we want. What we want is we want to have each pixel looking up a different position in our image. And the way that we can do that is we can just pass in this v coordinate. Okay. And now we're loading in an image. So what this is doing is each pixel, which has got a different v coordinate, is looking up a different position within our texture and then mapping it onto that bit of the canvas. So this isn't quite right, and the reason for this image being sort of up in the top right and being scaled in this way is just a difference in coordinate systems. So when you look up in a texture, then you're going from 0 to 1, whereas when you're in clip space, then you're going from -1 to 1. So you just need to do some kind of coordinate transform to get you from one world to the other, which is pretty simple. It's just a bit of maths. Okay, so hopefully that gives you an idea of sort of the basics of loading up an image in WebGL, showing it onto the screen. Now I'm going to get more into actual image manipulation techniques. So what is it that we can do on the graphics card to do all these techniques that you might know from image editing programs like Photoshop or something similar? So the first thing I'm going to look at is just scaling, translating, and rotating. Then I'm going to look at some simple color tricks. After that, I'm going to do some image warping, then some pixel effects, and then a little bit of blending. So first of all, scaling and translating. So you've already seen a bit of this. You've seen me scale the image. And let me just quickly change the program that I'm using, something more involved. Okay. So all I did there, I just swapped out the shaders that I was using for something which has got a few more kind of utility functions to make it easier to show you these demos. So for example, if we want to scale an image, then all we need to do is take the coordinates that we're sending out of this shader and multiply it by some sort of constant. So this is just multiplying this in clip space by some number, and as I change this number from something like 0.5 to 1, then it just grows. We can similarly move the image across by just adding to this number. So like this. And we can also do a rotation. So rotation is a bit more complicated. You need to use something called a matrix to apply to this vector. So I'm not going to explain exactly how that works. But I've just written a utility function which creates the right kind of rotation matrix and lets you apply it. So you can just rotate your image in the same way. So all this is doing is it's just moving our vertices. And then because the graphics card is doing all the interpolation for us, we don't have to worry about anything else. From the point of view of our fragment shader, we're still just drawing a square. It was just rotated before in the vertex shader. Okay, so now I'm going to move over to the fragment shader and show you some of the tricks that you can do using colors. So I have each pixel has the kind of color that I want to display loaded into this color parameter, which is output here at the end. And the simplest color trick you can do is just swap two color channels. So WebGL supports this kind of syntax where you can just write RGB and then you can write RBG, and it just is swapping these two color channels, so you don't have to kind of save it off into a temporary variable. And you can even do stuff like this where you just set everything to be one color channel, which gives you just the red channel, or this will just give you the green channel. Another trick that you can do is change the gamma of the image. So if you're like a graphic designer, you might have heard of this. So what this lets you do is it lets you compress the image more on the white side of the spectrum or on the black side of the spectrum. And this is nothing but some kind of raising of an image to the some kind of power. So we're taking each vector and we're raising each component of that vector to some sort of power. And depending on what number you put in here, then you're going to get an image which is kind of more sort of faded and white, or more kind of dark. So this can be quite useful if you have an image which was underexposed. Then you can change its color into something which is more kind of contrasty. Okay, so the next thing I'd like to show you is the ability to sort of segment out one portion of the image and apply just one filter to that. So I'm just going to change picture to this picture of a cat, where the background is very green, but the cat is very white. And you can use this to do a very sort of simple segmentation of that image. So for example, we can ask if this pixel has got a certain color. So if there's a lot of red in this pixel, then we can do something to that pixel. So I'm just going to connect this up to this UA slider so I can change the threshold. So what I'm going to do is going to say, okay, if the red channel is above a certain value, I'm just going to swap two components. And then as you change this, then you can basically selectively change the color of the cat. If you make it too low, then it changes everything, so it's just about finding the right threshold. But you can use this to kind of darken one bit of the image or lighten another one. I mean, similarly, if we just invert this selection, then it will just be changing the background. Or we could make it be, say, black and white, but keep the cat in color. Okay, so the next set of examples is a little bit more involved, but I think they're kind of a bit more fun as well. So far all we've been doing is just loading in the image and tweaking the channels, tweaking the values that we get out of it. But we can actually get some quite interesting effects if we change the way we look up pixels from our texture. So the way we look up pixels from the texture is that we have this UV parameter, which is closely related to our coordinate that we defined before. So this is something which is a vector, which is 0, 0 at the bottom here, and 1, 1 at the top. And if we change the value of this vector, then we'll change the way we're looking up within our image. So for example, we can say, if our x component is bigger than 5, then just clamp it to 5. So what this means is that all the pixels here on the left-hand side, where we're in a region where UVX is less than 5, they don't get affected. But when they're larger than 5, then we look up into the texture in such a way as if we'd been in the middle of the texture here, which gives us this kind of spread out blur for this half of the image. Now this is a little bit horrible. So what we can do is apply some kind of transformation which is a more smooth. So something which gradually changes across the whole image and gives us something that looks a bit different. So for example, we can square the value of x. And the effect of this is that it kind of squeezes the image to one side. This is because the values on the right-hand side are going to stay more or less what they were before, because if you square 1, you get 1. But if you're going to square a very small number, it's going to get a lot smaller. So the lookup is going to get compressed in this region. And we can, of course, do this with, we can just play around with different numbers, so we can sort of change one channel based on the other and make our image look pretty crap. What's more interesting is if we don't do this kind of scaling in the coordinate space of our image, but we instead switch to a new coordinate space, which is defined in terms of how far away you are from the center of the image and the angle at which you are from that center. So this is called a polar coordinate system, where your two parameters, rather than being x and y, are r and theta. And what we're going to be doing to kind of do some of these effects is we're going to start with UV, which is just our standard x and y coordinate. We're going to convert it to a polar vector, which is going to be r and theta. We can then do something with that polar component, and then convert it back into UV, and then use that modified component to look up our color from our texture. So the simplest trick is just the same one that I showed you a second ago, where we just square the first component. So in this case, we're squaring the radius. So what this does is it kind of makes the image a little bit too big. So we need to make it a bit smaller to make it look more like kind of a fisheye effect. So what this is doing is making all the pixels at the center, which have got a very small radius, they're going to be affected a lot, and they're going to get squished out from the center, whereas the ones on the edge, which are close to 1, aren't so affected. And this gives you this kind of fisheye lens effect. You can also, rather than deforming just based on radius, do a sort of a twirl. So this is something where the further away you get from the center of your image, the more you've kind of rotated it. It's as if you had like a painting and you kind of stretched it round some kind of pole or something like that. So to get this kind of effect, what we need to do is take not the radius, but the theta of our polar vector and transform it depending on how far away we are from the center. So just starting from a kind of a no-op, where we just take the theta and don't add anything to it, our image looks the same. If we add some kind of set component, some constant, then this just has the effect of rotating our image. So this isn't quite what we want. What we want is to rotate the image more when we're further away from the center. So to do this, we're just going to multiply this by the radius. That's the first component of this polar vector. And then as we kind of scale this, we're going to get this sort of twirl, swirly effect, because the pixels at the center aren't affected very much, because polar x is more or less 0 there. But at the corner, they're affected quite a lot because our radius is high. So we can also do similar effects, but rather than driving them from a constant, we can get some kind of periodic function into play and make our image kind of be deformed as if it was kind of ripples on a lake. So I'm going to first do this in this UV space, and then I'm going to do one in radial space as well. So the way this is going to work is that we're going to take, again, the x component, and we're going to deform it in some kind of way that is dependent on where you are in the image. So we're going to add some kind of small constant that's dependent on the sign of where we are in this image. And to make this look good, I need to multiply this by 10. Okay. Yeah. So what this sign function is doing is it's taking our x component, which goes from left to right from 0 to 1, multiplied it by 50, so it's 0 to 50. You run this for a sign function, and you're going to get something that's periodic, so something that, as you go across the image, is going to give you a number which is somewhere between 1 and -1. And then we're going to just scale it by this small value so it isn't too big. And if we hook this up to our sliders, so we can play with it, we can control sort of exactly how, it's a bit smaller, how much our image is getting deformed. So this parameter here will just change how big our waves are, and this one is going to change how frequent the waves that we have are. And we can also make the waves be in the y direction rather than the x direction to give this kind of more sort of up and down effect rather than left and right effect. And again, you can apply the same kind of function, but rather than using x and y, we can first transform to our polar space and modify things there. And that gives us this kind of effect. Okay, so the last section is on pixel effects and other effects, which I couldn't find a good section for. So first of all, I'm going to look at how we can take an image and make it appear pixelated. So by this I mean, how can we make it look as if we have kind of blocks of squares that go across the image, which are a lot bigger than the actual pixels that we have on our screen. So essentially what we want to do is make it so a whole group of pixels, say 50 pixels up here in the top corner, they all look up the same value from our texture. So the simplest way to do this is just to round to the nearest value. So if we do this, then all of our pixels are just getting rounded to 1 pixel. So this isn't what we want. What we want is for this rounding function to be not quite as granular. And the way that we can do this is multiply it by 10, and then divide by 10 out here. And then what this does is we kind of get a snapping effect to each pixel. And again, I can just hook this up to this parameter, and it just allows us to choose the size of our pixels based on the value of this slider. So what this is doing here is it's taking this UV number, which is a two-dimensional vector. It's scaling it by some number, so it's going to be, in this case, 35. So then across our entire field, we're going to have numbers from 0 to 35. This floor function is then going to cut off the fractional part, so we're going to get integers from 0 to 35, and then we're going to scale it back down to the range 0 to 1, so we can actually look up within our image. So just like I was showing you earlier with changing the background of the cat, we can use this to do kind of like a region pixelation. So I'm just going to load in a pixeled version of the image. So I just have a helper function here which just draws a pixelated version of the image using pretty much the same code I just showed you. So the value of image for each pixel is the kind of unchanged image, and the value of pixel is the pixelated image. So now what we can do is we can do some kind of query, and we can ask, well, if the pixelated image has got a high red channel, so again, this cat is mostly got red, and the background hasn't got any red, then we can set the color to be the pixelated version, and otherwise just keep it what it was before. So then as we change this slider, we can sort of slowly kind of pixel out our cat. And as we go even further, then we pixel out the background. So it's again about finding sort of the right in-between position. Okay, so I've got two more effects. So the first one is something called vignetting. So if you've used Instagram, you've probably put this on every other picture that you've uploaded to the internet. So this effect is where you try and make your image look kind of more old school by making the edges kind of blur out. And this is actually very easy to implement once you have this kind of radial coordinate system, because all you're really doing is saying, the further away I'm from the center of my image, the more I want to have some kind of dark color. So the way we're actually going to do this is we're going to use this function called mix, which allows us to basically mix two vectors or floats depending on some kind of parameter here. So if we set this to be 0, then it's just going to give us this color. If we set it to 1, it's just going to give us black everywhere. So as we change this parameter, it just lets us smoothly change between one thing and another thing. So if rather than hooking this up to some slider, we hook it up to something that's related to our position, then we can sort of cut out one bit of the image. And for this, we're going to use another function called step. So what this function does is it lets you sort of define some kind of threshold. And if you're above that threshold, it returns 1. If you're below, it returns 0. So that's exactly what we want. So here, what this step function is doing is it's checking this polar coordinate r and saying if it's below 0.5, so in the center here, then return 0. And the effect of that is then we pick color from this mix function. And if it's above, then it's going to pick this black color. So this isn't quite the effect that we want. What we want is some kind of more smooth step. And luckily, for that, there is a smooth step function. So this, rather than taking one parameter, takes 2. And sort of gradually, that was probably a bit too big, and gradually sort of smooths from one value to the other. So if you're below 0.5, then it will be the first color, so just the image. If you're above 0.7, then it will be the second one, black, and in between it's going to sort of give you an interpolation between the two things. And finally, we can use this mix function to just mix two images together. So up here, I've just got a gradient defined, which is drawing the gradient that I was just showing you earlier. And if I want to mix the image that we have here with the gradient, then I can just set the color based on something positional. So I can just take the gradients and use this step function, triggered off 0.5 like this. So what this will do is it will let us kind of mix two images together, left and right. And by changing the value of this, then we can sort of slide from one to the other. And we can do the same trick as with the smooth step to make it slightly less jarring. To kind of blend it in this way. Okay, so that's all the effects that I've had. Do you have any questions?
Pokud si netroufáte to formulovat v angličtině, klidně se zeptejte česky, já myslím, že vám Felix bude rozumět. Já bych ti dal ještě mikrofon, jestli chvilku vydržíš.
Hi, is it possible to download the result using frame buffer or something like to save it?
Yeah, you can just save it into a JPEG if you want. It's just one API call. Yeah. In this case, yes, but you can then take those pixels and do whatever you want with them. So you can change them from JavaScript, you can save them to a file. You could even then save them to another texture and send them into another kind of WebGL program. So you can get a whole pipeline going where you'd have multiple effects stacked on top of each other. Yeah, so in case someone else can't hear, the question is the output always to the pixels in that canvas? And the answer is yes. And that does make it quite hard to develop this kind of code because you don't have anything like breakpoints or logging. You just have a canvas. So if you want to figure out what the value of some parameter is, then you can draw it onto the screen. But that is about it. So the code that the question was, is the code I'm showing JavaScript? The answer is no. If you think this is JavaScript, then you've got a bit of a problem. So this is called GLSL. It stands for, I can't remember actually. But it's basically something that looks very much like C, but it has support for all these kind of three-dimensional primitives. So you can create vectors, you can create matrices, and you can sort of multiply them in a way that isn't painful, basically. So you can do like a number times a matrix, and it will kind of multiply element-wise. So it's actually quite a small language, and if you know a bit of JavaScript, then it's quite straightforward. Well, you need a graphics card. So the question was, can you use it outside of the browser? So you need some kind of graphics card to execute this code. So if you did have a graphics card available on your server that was running Node.js, I'm pretty sure you could run it, but I'm not sure. I don't know if I've actually tried it. Like, you might need to run some kind of headless browser to actually get it to work. I'm not sure if Node.js supports it directly. But definitely outside of the JavaScript world, then a lot of people in machine learning, then what they do is they write their code in Python, but then they use CUDA or other frameworks which let them execute the kind of calculations that they're doing on the graphics card. So it is definitely something that's being used outside of just visualizations. So the question is it hard to transform an OpenGL application to one in WebGL? Answer is I don't know, because I haven't done it. The shading language is very similar, like it is based on OpenGL. It doesn't have all the functionality that you have in kind of OpenGL 4.4, whatever they're on. It's similar to OpenGL ES. So I think a lot of your shaders, then you might not be able to use all the functions that you've had before, but if you're using kind of more of the basic functions, then you should be able to port it. Yeah. And there have been, I think Unity and similar tools do let you export to WebGL, but I don't have any experience with that. So the question was, does WebGL support other shading languages? And the answer is no.
Tak jestli už nejsou další?
So you can either just set up like an animation loop within JavaScript and update one of these values over time. So you could just use that by just updating something from 0 to some higher number, or you can use a library like tween.js, which will just change the value of something. So the way I have this code set up is that it re-renders every time this changes. But it's also rendering periodically, so that when I change this code in GLSL, it updates. So normally what you do is you can pass in a time, and then you can just animate stuff based on that. So it's pretty simple. So the question is, how reliable is WebGL across different platforms and computers, including from 1995? So from 1995, it won't work, I think, because that doesn't even have a graphics card. It has had problems historically, like any new technology. You need to kind of wait for it to get more support. It is now supported in all the major browsers on desktop, and as of like a month ago, it's supported on iOS as well, on both iPads and iPods, and iPhones, I mean. It is true that you can sometimes hit bugs that are specific to one operating system, and they can even have bugs which are specific to a single graphics card. So that does make it a bit painful. And there's often like extra features that you can or can't use, depending on what kind of hardware you have. So I've spent some time developing these applications, and what I normally do is I kind of try and look at what is supported on most people's hardware, and then use that. And there's quite a good website called WebGL Stats, which just crowdsources this information. So for example, I was uploading a texture to the graphics card so I can show this image, and there's a limit on how many textures you can have. Some graphics cards, like I think this one could do 16, but some can only do 8. So I think 90% can do 8, so you limit yourself to 8, because you want it to work on as many platforms as possible. But yeah, it's quite difficult. Like, it is kind of cutting edge technology, but I really think that now it has got a lot of support. Like, you're not just going to be supporting like a couple of Macs in Silicon Valley. Like, it is a lot of people's computers. So.
Tak to byla asi už poslední otázka, protože už jsme trošičku přetáhli čas a už vidím Štěpána Bechinského, který si přichází se svými hardwarovými hračkami na další přednášku. Takže já děkuji Felixovi za skvělou přednášku a za chvíli začínáme s další přednáškou.
Thanks.